Greetings, everyone. All right, this is the next part of section 5.1, and it follows the video that I titled Defining Area Bounded by a Curve, which I did not put that was section 5.1 in its title, but that's okay. So we want to now see about an application for area under the curve that we're going to be using quite frequently. And in fact, it's an application that was used or is commonly used in pre-calculus. And so this perhaps is going to be a review for you, but I do want to talk about it and get us established on this. So if it's a refresher, good, and if it's brand new, so be it, but I think you'll follow along. So, we just defined in the previous video how to calculate the area under the curve. And so let's take a really simple curve. In fact, it's just a horizontal line, and I'm calling it the output of 4 from the interval from 0 to 5. And notice the units on the axes here. So we have time in seconds on the horizontal axis, and we have velocity in meters per second on the vertical axis. So we're looking at a velocity versus time graph. And in looking at this velocity versus time graph, I want us to understand and interpret what we mean physically for the motion of the object by this area under the curve. So remember, an object that has a positive velocity is moving in a certain direction, usually to the right, but it could be upward. It depends on what kind of motion we're describing in the moment. So we're talking about a constant velocity of 4 meters per second for 5 seconds. And so the object's moving straight, not changing direction, not slowing down or speeding up, moving at a constant rate for 5 seconds. And so like in pre-cal, we would find the area bounded by this curve to figure out something about the motion of the object. You probably already have an idea of what we're figuring out, but I don't want to mention it just yet. So, of course, since we're dealing with a rectangle here, what we would do algebraically to calculate this area is we would multiply, let me change a different style of pen here. The area would be just 4 times 5, which would give us 20. But if we stick with just the raw numbers without the interpretation of what they mean, then we're losing something here. And so let's go back for a moment and do the same calculation, but let's think about the units involved as well. So we said that the object was moving at 4 meters per second, and it was doing so for 5 seconds. Well, of course, we do get our 20, but let's take a look at the propagation of the units here. We have meters per second times seconds. And so if we go, do the basic algebra here of canceling the seconds out, then we're left with the answer as just 20 meters. And so what did that area under the velocity curve tell us? Well, it tells us the distance that the object traveled during those 5 seconds. So it says that the object traveled 20 meters in those 5 seconds. So this area under here represents for us, I'm going to phrase it this way, something related to the distance of the object, or something related to the distance at which the object traveled for those first 5 seconds. And I'm phrasing it that way because we are going to modify this relationship a little bit, make it a little bit more precise for different contexts. That's in a later section. This is just the introduction right now, really a reminder from the pre-cal relationship. So again, the area bounded by the velocity curve is related to the distance traveled by the object on the time interval given. All right, so again, all I did is multiply base times height here because we're dealing with the area of a rectangle. And in doing so, I was able to multiply the units together in a way to get the time to cancel here, the seconds to cancel, and be left with the units of meters on the number. And then I just interpreted what that meant in the context of the problem. As a side note, if and when you take physics, looking at the unit analysis, which is how the units simplify algebraically, can give you a really strong clue about what you're trying to solve in the problem, or what you're solving for in the problem, or if you're solving for a particular value and you know the units of that value, that could help you properly set up the mathematics to solve that problem. So unit propagation like this, unit analysis, is an important part of applying mathematics to a situation. So it's something to become familiar with and use to your advantage when necessary. Now let's try to generalize this to a curve like we've been talking about here. Let's suppose we are looking at another velocity curve, okay? And so the velocity curve that we're looking, looks like the other one that we had in the other video. We would calculate the area in the same 5-step process that I described before, but I want to focus on one particular slice. And I drew that little slice bigger than I did in the last video because I just want to emphasize what's going on here. To approximate the area under the curve, we can again use rectangles, and if we want to take a look at the rectangles that we're using here, what do the pieces of the rectangle in which we're finding the area of to approximate the actual area represent? Well, this little horizontal displacement here, delta x in the previous video, but in this case, since time is our horizontal axis, this would be delta t. So this represents a time value here, okay? Or at least let me rephrase that. This represents a change in time, and so the units are still the time units in that direction. What about the vertical side, or the height of this rectangle? Well, if we call our velocity function v, then this is going to be v of t star, just to keep consistent with that previous notation, where t star is just some t value on this interval. I'm using a left-hand rectangle here in the picture, but it doesn't really matter for the concept here. So the height is just some output of the velocity function. So again, in finding this area, if I take a look at the units in the analysis here, the area that we're trying to find, okay, the vertical side of the picture here is a velocity value, which is given in meters per second. And I'm just going to look at the units and do the unit analysis here. The horizontal side is a change in time, which has a unit of seconds on there. So finding the area of the rectangle, I'd be multiplying some velocity in meters per second times some change in time, which is in seconds. And then again, when we do the algebra here of crossing this, of canceling these two values out, we'll be left with the units of the distance, which in this case is meters. And so even if we're dealing with motion that's not constant, okay, then the area that we're finding bounded by this curve is still going to give, by this velocity curve, let me be clear about that, the area bounded by this velocity curve, the time axis on some interval of time, is still giving us something related to the distance traveled by the object. Now notice the velocity curve that I gave is always positive. It could have been 0. As long as it remained non-negative, what I'm saying still is true. But the object does, since the velocity curve is always non-negative, the object doesn't change direction. If the object did change direction, then the area bounded by the curve is going to have a slightly different meaning, which we will be developing in a later section. So I'm just pointing out that the curve that we're dealing with has positive values only in this case, and so the object doesn't change direction. And so when we calculate the area under this curve, we are getting the distance traveled by the object. But that's going to change when the object has the opportunity to change direction. Then we'll have to have a slightly different interpretation of a couple different graphs that we're going to be representing those situations by. So now let's suppose we're dealing with an acceleration versus time graph. What would the area, or how would we interpret the area underneath this curve between this time interval? How would we interpret it? At least, what would the units be? The actual interpretation, we'll develop that over time, but what units would it have? Well, of course, we would be dealing with another rectangle as a way of approximating it. Let me get a better rectangle here. So how about this one? And using a similar mindset here, this horizontal side is still going to be our change in time. And this side over here is now going to be a of some t star, some value of t in our given interval. It's an acceleration. And so if I go to calculate the area of that rectangle, I'm going to be using the height units, which are in meters per second squared. And then I'm going to multiply that times the horizontal dimension, which is going to be in seconds. And then when I simplify this, we're going to get meters per second after we do some canceling here. So this one is going to cancel with one of those, leaving just meters per second. So that means the area under this curve here is related to the velocity of the object, so because the units are in meters per second. So this unit analysis gives you a way of interpreting what the area represents in the context of the problem. So you have to pay attention to the units on the axes. And when we're finding the area bounded by by that curve and the axes, then we need to multiply those units together, see what kind of units result, and then make an interpretation based on that. Now I'm leaving some of the interpretation for a later section because there are some things that we need to understand in a little more detail, and we're going to do that over the next couple sections. We'll come back to this concept again, but this is a good introduction for you. So we'll leave it there for now. Go study.